Yeah, so I'm Maurice. I'm presenting our work on provable robustness against backdoor attacks. This has been joint work together with Xiaojun, with Bojan, C, and Bo from UIUC and us from ETH. Okay. So when we talk about adversarial robustness, there's largely two types of attacks that we can consider. So on the one hand, we have evasion attacks. And this kind of attack happens when an adversary tries to attack a trained model during deployment. So an adversary tries to craft an adversarial example that tricks a model into making a wrong prediction, for example. So in this example, we have a gibbon so an image of a gibbon, and if you add some adversarial noise, then this is going to be classified as an airplane, for example. And then there's another type of attack, which is data poisoning attacks. And this is the focus in this work. So here, what an attacker aims to do is they aim to either manipulate a data set or a training process by, for example, injecting patterns into the training instances, which lead to a classifier or a machine learning model that associates this trigger, this backdoor trigger, with the wrong class, basically. And this becomes arguably a bigger problem when data sets become larger and cannot be curated manually by the defender. And there's two things that I would like to mention here. On the one hand, we have empirical defenses against data poisoning attacks, where there has been a lot of research. And then there's also certified robustness. And this is what we are trying to do here. So what we are doing is we want to make the statement that whenever the attack satisfies certain conditions, then the attack is guaranteed to have failed. Okay, so to give you a brief overview, I will start with the threat model and the defense goal, and then present the method overview, and finally, and the robustness guarantee, and finally, some experimental evaluations. Okay, so what is the threat model? The setting that we consider here is that an attacker or an adversary attacks a classifier and a training set, so classifier H and the training set D. And the capabilities of the adversary are that they can alter either features, and so they can alter features by injecting those patterns. So, for example, those white triangles, and they can flip labels. So they can flip the label of an image of a dog to a lion, for example. And the second capability that the attacker has is they can replace a certain number of training instances with the backdoored or altered samples, and by this process create a backdoored training set. What we do not assume is that, so we assume that the attacker cannot interfere with the training process here, for example. And we say that the attack succeeds if, on a certain test example, the attacker can guide the model prediction. So if the attacker knows the backdoor pattern and adds this backdoor pattern to the input, on a classifier which was trained on a backdoor training set, then they can control the model prediction. So, for example, if we have a training set consisting of images of dogs and lions, then the attacker adds those triggers to images of lions, for example, and flips the labels to be dogs. And then, if during deployment they add this white triangle to an image of a lion, then they can control the prediction into fooling the classifier to believing that this is an image of a dog. At the same time, if the attacker does not add the pattern, if it's a clean test example, then the classifier or the model performs as expected. So there's not a decrease in clean accuracy, and this makes the attack particularly vicious because it's difficult to spot. So now the defense goal. The goal is to ensure that the predictions of the backdoored model are independent of the pattern. Because then if we can say that those predictions are independent of the pattern, then it is known that the attacker does not have any additional information by simply knowing the pattern. So they cannot guide the model prediction. So, or more formally, the guarantee that the statement that we want to make is we want to say that whenever you have a classifier which was trained on a backdoor training set, and the classifier receives the the input with the backdoor pattern, then the classifier would have made the same prediction if it had been trained on a data set without the trigger. So what we don't do here, so this is what we do. What we don't do here is we don't defend against label flips. So the classifier could still make a wrong prediction because of label flips. But it still means that the attacker cannot have any additional information by knowing the pattern. Okay, so and the method overview. So how we achieve this guarantee is we generalize randomized smoothing from smoothing over testing to smoothing over the training set. So what we do is we take a Poisson training set, we create n different versions of this training set by adding noise to each sample, and then train an ensemble of n different models and aggregate the prediction to get the final robust prediction. And the intuition is that, so the statement that we want to make is on a high level is if the backdoor magnitude is small enough, then the attack is guaranteed to have failed. And more formally, this means that given we have a backdoor training set, and if the radius or the magnitude of the backdoor pattern is smaller than a certain amount, then it is guaranteed that the attack has failed. Now, the question is, how do we find the radius R? Because this is what we need in order to get the certificate. And yeah, the answer here is randomized smoothing. So to give you a brief overview over this, we basically view a machine learning model prediction as a function, as a deterministic function of a test instance X and the training set D. And then given a base classifier G, the smoothed classifier, so smoothed over the training set, is given by the expectation value of the classifier with respect to training sets augmented by noise. And yeah, as I said, this is similar to the classical randomized smoothing approach, but instead of smoothing over test instances, we smooth over the training set. And the result that we obtain here is this. So if we use Gaussian noise to smooth the model, and we have a Poisson classifier that predicts a certain class, let's say A, with a probability PA, and the runner-up class, so the second most likely class, with another confidence PB, then if the backdoor pattern, if the magnitude of the pattern is bounded by this quantity, which depends on the smoothing variance and the number of backdoored instances R, then it is guaranteed that the attack has failed. So to make this operationally, to operationalize this result, what does the defender need to know? So first of all, in order to evaluate this certificate, the defender needs to have knowledge about at least an upper bound of the backdoor magnitude omega in L2 norm. And the second ingredient that the defender needs to know is knowledge about how many samples have been poisoned, or at least an upper bound over how many samples have been poisoned. And finally, this is part of the threat model as well, that the defender needs to have full control over the training process, or put differently, the adversary cannot interfere with the training process. Now, there's one caveat here. If we would directly apply this result to certify robustness, which is the distribution mismatch. So directly applying smoothing does not work. And the reason is that basically if we augment all those training instances with Gaussian noise, then the classifier has only seen Gaussian noise augmented training samples during training. And this is challenge number one. And the challenge number two is that the model needs to be deterministic. So this makes it impossible to simply add random noise to test instances, because we need to have a deterministic model in the input X and in the training set D. Otherwise, the theorem does not hold. And the solution that we came up with here is what we call model deterministic test time augmentation. And here, what we do is we take, so the input is an image X, for example, and the data set D, and then we train a model, and based on the train model, we compute the hash of the model file, and use this hash as a seed for drawing a random noise vector from the normal distribution. And then we store this noise vector together with the model in order to add it to the test instance during inference. And then we alleviate this mismatch between training and testing distribution. And at the same time, we still have a deterministic function in the input x and the data set d, because the data set deterministically determines deterministically the hash of the model. So we also ran a few benchmark evaluations on different data sets, on vision data sets and on tabular data sets. So in this talk, I will highlight the results on the vision data sets, on MNIST, Cypher10, and ImageNet. So this ImageNet is a 10-class version of the original ImageNet. It's a smaller version of the original ImageNet data set. And we consider 3 different backdoor attacks. So we consider a 1-pixel attack, a 4-pixel attack, and a blending attack. And we inject between 5 and 10% of backdoored instances into the training set. So to go through the results quickly, the first observation that we can make here is that both the vanilla model and the RAB defended model have similar accuracy on clean instances. So we have between around 90% accuracy on MNIST, 60% on Cypher10, and 90% on the small ImageNet. At the same time, now we also consider empirical robust accuracy in order to compare with methods that empirically improve robustness against backdoor attacks. And for that, we evaluate the empirical robust accuracy only on instances that have been successfully backdoored against the vanilla model. And these are these results here. So here we ask, how does RAB compare with the state-of-the-art empirical backdoor defenses? And what we found is that even though RAB is not designed as an empirical defense, it can still achieve similar or comparable performance to the baseline methods that are designed for empirical as an empirical defense. And finally, and this is the strong thing about the RAB pipeline, is that we also provide certified accuracy. And this here means that, so those figures here mean that, for example, if we have 24% certified accuracy, then that means that not only were the examples which were successfully backdoored on the vanilla model, they were not only correct, but they were also guaranteed to have not been affected by the backdoor. So that they are guaranteed that the backdoor attack has failed on those examples. So to conclude, we made several contributions. So first of all, we proposed a framework to certify robustness against different backdoor attacks. We provided a pipeline to both empirically improve the robustness and to provide non-trivial certified robustness. And finally, we also introduced a trick, which we call model deterministic test time augmentation, that makes the defense really work in the first place. And what I've not touched upon here in this talk is we also proposed an exact and efficient algorithm for certified KNN, which alleviates the need to do Monte Carlo sampling to evaluate the models. Now, there's also limitations of this work. So the first is that RAB introduces a significant runtime overhead because we have to compute an entire ensemble of models. So for ImageNet, for example, we trained 200 models, and for the other data sets, we trained 1,000 models. And this, of course, while it's parallelizable, it still introduces a significant runtime overhead. And the other limitation that we have here is that RAB only certifies robustness in terms of the magnitude of the backdoor pattern, but not against label flips. And this, I believe, is also is super exciting future work, because you can look into how you combine different techniques to certify robustness against label flips and robustness against the magnitude in the backdoors. So with that, I would like to thank you for your attention, and I'm happy to take any questions.
Thank you for your talk. It was very interesting. I had a question. Why do you, maybe this is a dumb question, and if it is, please tell me, but why do you train n different models with the smoothing? Why not modify the data set n times, but just train a single model?
How do you mean by training?
So with your technique, you create n versions of the data set that are all with a small epsilon, like they're all modified in some way.
Yeah.
Then you train n models and you aggregate them.
Yeah.
And I was wondering why you don't take all that data that's been modified and just train a single model instead of training n models.
Ah, I see. Yeah, so good question. So this is because we compute an expectation over different classifiers, essentially. So this, maybe I can go back quickly. So here in the right corner, right upper corner, we have an expectation over different classifiers, essentially, because a different model leads to a different classifier. So the different noise added to the model leads to a different classifier, and we average over all those classifiers.
Okay, thanks.
Hi, great talk. This is Li Min from IUC. I have a question about the label flip. I was thinking that there are some recent backdoor attack that provide kind of clean label attack. They do not change the labels of the pointing sets.
Yeah.
Do you think that there are some kind of related work about the certified robustness against such attack?
Yes. So I mean, this work here can also be used for that, as long as those kind of attacks don't interfere with the training process, right? So if you have a clean label attack and the attacker wants to, for example, map different inputs in latent space to the same cluster, then this results in interfering with the training process in the end. And then you cannot use this example, this technique, for example. I'm currently not aware about any technique that would also allow the attacker to interfere with the training process. So this I'm not aware of that.
Okay, thank you.
Thank you.
Okay, probably the last question.
I wonder what would happen if the magnitude of the attack distributed over the image, like, for example, 4 pixels, each one on the corner, in one of the corners of the image. Would you still have this, even if the magnitude is the same? Because now the shape and the pattern of that will be different.
So you're saying that, okay, I see. So basically, what you're asking is whether if the attacker changed the pattern during inference from, let's say, 4 pixels to 10 pixels, for example, or.
It could be 4 pixels, but not necessarily in the same case. I mean, next to each other, maybe 1 pixel on each corner of them.
I think then probably the backdoor attack could not be as effective, because you then have a different pattern during training versus during deployment. So the attacker could not exploit those biases that the model has learned from the original pattern. So is that what you're saying, that the attacker would change the pattern from training to testing, or if you would consider an altogether different pattern? Ah, yeah, okay. Yeah, so I mean, then in the end, what we simply need is that the overall magnitude of the pattern needs to be bounded. So if you consider a different attack here, then that also works with this defense. So if you have different patterns.
I don't understand what do you mean by magnitude.
By magnitude?
Yes. The number of pixels?
No, the magnitude is in L2 norm. So the difference between the distance between the backdoored instance and the clean instance, basically. So if you subtract the two, then you get the pattern, and the magnitude here is the L2 norm of the pattern, of the difference between the two examples. Does that answer your question?
So thank you very much again.
Thank you.
Thanks to the speaker again. Yeah. Okay.